she had students of 5 different age groups in the same class. Trying to teach different subjects and handle different levels of complexity for each student would result in a lot of confusion. Students in a school are allocated to classes based on the age group they belong to. It is because students in a class are likely to have similar attributes in terms of the level of knowledge, capabilities, height, and weight. Similarly, there are over 100 elements known to us. Scientists felt the need to classify them on the basis of some common properties. In this lesson, we will learn how the attempts to classify elements led to the evolution of the periodic classification of elements. At the end of this lesson, you will be able to examine early attempts at classification, analyze Dobbinia's law of triads and Newland's law of octaves, compare the merits and demerits of the law of triads and the law of octaves, list the main features of Mendeleev's periodic table, and analyze the merits and demerits of Mendeleev's periodic table. The earliest classification categorized elements into metals and non-metals. However, this classification served only limited purpose because of the following reasons. The classification was at a very broad level. A large number of elements were classified as metals. However, they did not necessarily display similar chemical properties. For example, sodium and copper were both characterized as metals, but their chemical properties are very different. Some elements, such as boron, exhibited the properties of both metals as well as non-metals. It was difficult to determine how to classify such elements. After further research, a German scientist, Dobbinia, arrived at a hypothesis in the year 1829. According to Dobbinia, all elements occurred in groups of 3 when arranged in increasing order of atomic masses. He referred to these groups as triads. Dobbinia's law of triads states that the atomic mass of the middle element of a triad is the arithmetic mean of the atomic masses of the other 2 elements. To illustrate this law, consider the triad of lithium, sodium, and potassium. The atomic mass of lithium is 7, the atomic mass of sodium is 23, and the atomic mass of potassium is 39. The arithmetic mean of the atomic masses of lithium and potassium is 23. This is equal to the atomic mass of sodium. Similarly, in the triad of chlorine, bromine, and iodine, the arithmetic mean of the atomic masses of chlorine and iodine is approximately equal to the atomic mass of bromine. While this law worked for some elements, it was not a success because all the known elements could not be arranged in the form of triads. The law did not hold good for elements with very low or very high atomic mass. For example, the arithmetic mean of the atomic masses of fluorine, 19, and bromine, 80, which comes to 49.5, varies significantly from the atomic mass of chlorine, which is 35.5. Since Dobbinia's law could not successfully group elements, the attempts at classification continued. The next attempt came in 1864 when an English chemist, John Newlands, stated his observations in the form of Newland's law of octaves. Newlands noted that when elements are arranged in increasing order of their atomic weights, the property of every 8th element is similar to that of the first element, similar to the first and the 8th notes in the musical scale. Consider the list of elements with their atomic weights in increasing order. Starting with lithium, the 8th element from lithium is sodium. Similarly, the 8th element from sodium is potassium. Lithium, sodium, and potassium show similar properties. For example, they are metallic in nature. have high reactivity and conduct heat and electricity. Similarly, beryllium, magnesium and calcium show similar properties. For instance, all the three elements are shiny and fairly soft. However, Newland's law of octaves failed, because it was not valid for elements of atomic masses higher than calcium. Newly discovered elements could not find a place in Newland's table. Mendeleev based his work on the research by Newlands and took it further. He felt that effective grouping of elements and prediction of properties could be based on two parameters: atomic weight and chemical reactivity. Mendeleev's periodic law states that the physical and chemical properties of all elements are a periodic function of their atomic masses. Let's look at the features of Mendeleev's periodic table. The table had 8 vertical columns called groups and 12 horizontal rows called periods. In every group, a gradation of physical and chemical properties of elements was observed. The table provided gaps for undiscovered elements. The table helped predict the properties of 3 elements. These elements were named Eka, boron, Eka, aluminium, and Eka, silicon. When these elements were discovered, they were named scandium, gallium, and germanium. The properties of these elements were very close to those predicted by Mendeleev. Like other attempts at classification of elements, Mendeleev's periodic table also had some merits and demerits. Let's take a look at the merits first. The table helped in the correction of atomic mass for many elements. It predicted the existence of some elements that had not been discovered at the time that the table was created. Because of its merits, the periodic table is widely accepted as a system of classification. However, it did not achieve complete success because of some demerits. The table had some inaccuracies. For example, the table reversed the atomic weights of 2 pairs of elements. A. Iodine, with atomic weight 127, came after tellurium, with atomic weight 128. B. Nickel, with atomic weight is 58.68, came after cobalt, whose atomic weight is 58.94. Alkali metals such as sodium and potassium, and coinage metals such as copper, silver, and gold were placed in the same group, even though their properties are significantly different. Lanthanides and actinides were not given proper place in the periodic table. Isotopes did not find a place in the periodic table. The table did not clearly indicate the position of hydrogen. H. J. Moseley, an English physicist, built further on the periodic table to resolve the problems encountered in using it. He discovered that atomic number is a better basis for classifying elements than atomic weight. On the basis of his work, he developed the modern periodic law. The modern periodic law states the physical and chemical properties of all elements are periodic functions of their atomic numbers. The modern periodic law has become the universally accepted form of classification of elements, as it does not suffer from the demerits of Mendeleev's periodic table.